So the first part of the fundamental theorem of calculus said that if we take an integral and then we take the derivative, we get back to where we started, and so derivatives and integrals are, in a sort, inverses of each other. And they're only truly inverses in very specific situations. There were times we had to use the chain rule, and we had to use those properties of integrals so that we could separate them. But they're essentially inverses of each other. The second part says the same thing, but it says it in another way. Instead of taking the derivative first and then the integral, we're going to do it. I'm sorry. Instead of taking the integral first and then the derivative, we're going to do it in the opposite direction. So here's what the second fundamental theorem says. The second fundamental theorem is also known as the integral evaluation theorem. And not that the first one is important, not that the first one is not important, but the second part of the fundamental theorem is way more important because it allows us to evaluate definite integrals without using our calculator. And without using limits on Riemann sums over and over and over again. And I know you guys just love doing that. So here's what the second fundamental theorem says. If f is a continuous function on some interval, and big F is any antiderivative. You guys remember what antiderivatives are, right? Antiderivative is a function that if you differentiate it, you get back to the original function. So big F is any antiderivative of f on that interval. Then the integral from a to b of little f is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. This one is very closely tied to the first part. I don't know if you guys noticed, but I put on the first part, it's a corollary to part 2. Did you guys notice that? Probably not. Maybe you did. If you put x in where the b is, then this integral from any constant to x of f of x is going to equal big F of x minus big F of a. And then if we took the derivative of that, if we took the derivative of big F of x minus the big F of a, well, that big F of a is going to be a constant, and we end up getting back to the original function. So what this says is, if we take the antiderivative of this, well, it shows us that the derivatives and the antiderivatives are closely related to the integrals. And that we can use these antiderivatives to evaluate integrals, which is another way of saying that they're inverses of each other of sorts. This is an antiderivative that we evaluated yesterday on the calculator. You guys remember that?
Yes.
Okay. Let's go ahead and evaluate that using the second fundamental theorem of calculus. And this is going to be a procedure that we're going to use a lot over and over and over again. The first thing we need to do, we recognize here that our little f of x is going to be x squared. So our big F of x is going to be an antiderivative of little f of x. Well, what would the antiderivative of x squared look like? X to the third over 3, or 1/3 x to the third power, right? Plus c. Well, the theorem said any antiderivative. And since I can choose any antiderivative I want, I'm going to choose the one where c equals 0 and just get rid of it. Okay, this is an antiderivative of x squared. So this is going to be equal to big F of 5 minus big F of 1. Well, big F of 5 is going to be what? Just don't try to evaluate it yet. Just tell me what we get when we plug it in. 5 to the third power divided by 3 minus 1 to the third power divided by 3. 5 times 5 times 5 is 125 over 3 minus 1 over 3, which is 124 over 3. Anybody remember what we got yesterday? So this second fundamental theorem gives us a tool to evaluate these definite integrals without Riemann sums, particularly without limits on Riemann sums, and without using the calculator, which means that it could go on the non-calculated part of the test. Just like any other problem that we've done, I showed you a slightly lengthier way of doing it. If you were going to do it that way, that would be fine, but you would have to, on your paper somewhere, show what your little f is, what your big F is, and then show that you're evaluating big F at those 2 points. What we're going to do here is we're going to write it this way. The antiderivative that we're going to use of x squared is what we used before, x to the third over 3. And we're going to evaluate that at x equals 5 and x equals 1. So this is replacing what we wrote, big F of x equals x to the third over 3, and big F of 5 minus big F of 1. So this right here, this notation replaces all of this. So we write the antiderivative, we write this vertical bar that means evaluated at or when, and now we're evaluating it at 2 different places. So we have our upper limit and our lower limit, and then we go ahead and evaluate that. So that's going to equal 5 to the third over 3 minus 1 to the third over 3, and you go from there. Does that make sense?